Shall we begin?
Yes.
Okay. Hello everyone. I welcome you all for the sixth lecture by Professor Kenji Sugisaki. Today's lecture is on adiabatic quantum algorithms, and it will cover topics such as the adiabatic theorem, quantum annealing, adiabatic state preparation, etc. So, Professor Sugisaki.
Thank you very much. So, welcome to the lecture series of the quantum chemistry on quantum computers. And today's topic is adiabatic quantum algorithms. We already, in the previous lectures, we already studied about the quantum phase estimation and VQE. Both of them are based on the gate model quantum computing. Adiabatic quantum algorithm or adiabatic quantum computing is, of course, can also be carried out by using gate model quantum computers, but the computation strategy is somewhat different from the algorithm we already studied about in this field. So let us start by referring the adiabatic theorem. So let us assume that we have a system in the eigenstate of the time-dependent Hamiltonian Ht at t equals 0. So we have some eigenstate of the inside Hamiltonian. And throughout this talk, I usually refer this eigenstate is ground state, but generally adiabatic theorem is very general, so it can be applied to not only to the ground state but also the ecstatic state. But anyway, we have an eigenfunction of the Ht at t equals 0. Of course, the conventional QPE-based approach, we think about the time evolution of the time-independent Hamiltonian. But in this case, we think about the time evolution of the time-dependent Hamiltonian. In this case, the time evolution is governed by the Schrödinger equation. So here is a time-dependent Schrödinger equation. If the variation of the Hamiltonian Ht is sufficiently slow, in that case, the system is approximately in the ground state, eigenstate of the Ht at t is rather than 0. So basically, if the change of the Hamiltonian is very slow, the quantum state is in the eigenstate of the instantaneous Hamiltonian. This is the adiabatic theorem. So let's think about the initial Hamiltonian, H ini. We have eigenfunction of the this H initial Hamiltonian. And let us think about the Ht is a linear combination of initial Hamiltonian and final Hamiltonian. This final Hamiltonian is usually the problem Hamiltonian we want to solve. Let us define this Ht is the scheduling function. Usually is set to be t divided by large t, where large t is the total evolution time. So roughly speaking, t varies from 0 to 1. Sorry, Ht varies from 0 to 1. So if the Ht equals 0, in this case, this time-dependent Hamiltonian is just an initial Hamiltonian. But if time proceeds, the contribution from the final Hamiltonian will increase. If Ht equals 1, in that case, this time-dependent Hamiltonian is represented by just a final Hamiltonian. So this is a basic idea. The simple example is I think the simple example is one qubit system, or or spin 1/2 system. Let us think about the initial Hamiltonian is given by minus omega divided by 2 times power x. The ground state of this initial Hamiltonian is, of course, plus x direction, which is represented in the series 1 divided by square root 2 and linear combination, so plus 1 state. And the eigenvalue of the ground state is minus omega over 2. And let us think about the final Hamiltonian. It's the power 3 with the same question as the initial Hamiltonian. Of course, the ground state of this final Hamiltonian is, of course, upstate or close state, with the eigenvalue is, again, the minus omega divided by 2. Let us think about at the time t equals 0, the system is in the ground state of h inch. In the ground state of this inch Hamiltonian. So at time t equals 0, we have the eigenfunction written action here. And what happens if the Hamiltonian suddenly changes from inch Hamiltonian to final Hamiltonian at time t equals t0? This is the non-adiabatic case, of course. So the initial state is plus x direction. And the system Hamiltonian suddenly changes to this power 3 operators. This problem is very famous. I think most of quantum chemistry textbooks deal with this problem as a spin 1/2 problem. If the Hamiltonian suddenly changes from h init to h fin, in that case, the quantum state rotates around the axis. So initial state is the plus x direction, but if time passes, it goes to the plus y direction and minus x direction and minus 1 direction, and so on. And this is the case of the non-adiabatic cases. But if the Hamiltonian slowly changes from h init to h fin, again, let's start from the x direction, plus x direction. And in this case, the Hamiltonian slowly changes, and this can be understood by the continuous change of the direction of the external magnetic field of the, and let us think about the spin 1/2 such an electron. And the initial state can be realized by applying the external magnetic field along x-axis. And if the Hamiltonian slowly changes, so this can be realized by changing the direction of external magnetic field from x to z-axis. They gradually changes from x-axis to z-axis. The quantum state will follow the direction of the external magnetic field. So this is just a slowly changes of the contact axis along x-axis to z-axis. So if the variation is very slow, such as this quantum state will follow the change of the Hamiltonian, and finally we can obtain the power plus z state. So adiabatic quantum computing is based on this kind of approach. So we have a initial Hamiltonian and final Hamiltonian, and we also have to have a ground state or eigenstate of the initial Hamiltonian. and then perform it, and then the Hamiltonian will change the Hamiltonian very slowly from H any to H fin. So adiabatic quantum computing was basically this idea was proposed in this paper. The evolution of the time, the evolution of quantum state is governed by a time-dependent Hamiltonian that it can provide between an ancient Hamiltonian whose ground state is easy to construct. In this case, in this paper, they refer the ground state, but basically this can be any eigenstate. And the final Hamiltonian whose ground state encodes the satisfying assignment. So in this case, the adiabatic quantum building can be studied by any eigenstate, but usually the problem Hamiltonian, we construct the problem Hamiltonian, so that the eigenstate, sorry, the ground state of problem Hamiltonian is some kind of map of the problem we want to solve. So usually we start from the ground state to apply this adiabatic quantum computing to obtain the ground state of the problem Hamiltonian. And also, very importantly, adiabatic quantum model and the conventional quantum computation model are polynomial equivalent. This was proved in this paper. So polynomial equivalent means that basically the adiabatic computation model can be translated to the conventional quantum computation model with a polynomial overhead and vice versa. So basically, the problem that can be solved using the conventional quantum computation model can also be solved by using adiabatic computation model. So let me briefly summarize the idea of adiabatic quantum computing. So we have a time-dependent Hamiltonian, H3, which is a linear combination of H any and H fin, and Ht is a scheduling function which will vary from 0 to 1. And usually Ht, this scheduling function is we use the linear function as a scheduling function. So let's think about the situation that the total evolution time is large T. In this case, St equals small t over large T. And of course, by changing this scheduling function from 0 to 1, the energy of the ground state and also excited state can be changed. Like this schematic view. Important. This H fin is the Hamiltonian of the problem we want to solve. And H any is the initial Hamiltonian of which ground state can be prepared easily. An important thing is this initial Hamiltonian and final Hamiltonian should be uncommute. Because if two Hamiltonians are commute, they have Hamiltonian eigenfunction. So ground state of H any is some kind of the eigenstate of H fin in this case. So if the H any and H fin commute, so we have to check that the H any should be uncommute with H fin. And then we start from the usually the ground state of the initial Hamiltonian and changing the scheduling function St equal small t divided by t very slowly. And if the variation of Hamiltonian Ht is very slow enough, we can obtain the ground state of S thing at time t equals t. So, but the problem is how thoroughly we have to simulate the time evolution. There is very famous condition, I mean, for to set the evolution time. Let us think about this psi S is the instantaneous eigenstate of the Hamiltonian HS, time-dependent Hamiltonian HS. And this is a psi J is a ground state. Let us think about ground state. And this psi J is the excited state. And this EJ and E0 are eigenenergy of the instantaneous Hamiltonian with of HS. The evolution time should be sufficiently larger, longer than the maximum of this equation. So this the numerator is just the energy gap between the ground and excited state, and this denominator represents how variation Hamiltonian will result in the in some combination of the excited state from to the ground state. But also, it should be known that this equation is approximate in the sense that it doesn't result in strict inequality. Roughly speaking, this evolution time t must be lengthened inversely proportional to the square of the energy gap between the ground and excited state. So, if the energy gap between the ground and excited state is very small, in that case, we have to simulate the time-dependent, the time evolution under this time-dependent Hamiltonian very slowly. But if the energy gap is very large, in that case, we can sweep the time evolution very fast. So here I will give you an example of factorization of training one. So let's think about the prime factorization of training one. Of course, we can easily calculate. This is just 3 times 7, but let's think about it. I mean, the training one equal x times y. And in this case, we can map the x value and y value by using 3 qubits. X value can be mapped by using 1 qubit. And y is using 2 qubits. And final Hamiltonian can be defined like this: 21 minus xy squared. So in this case, if x times y equals 21, in this case, the ground state energy of the final Hamiltonian is 0. If we substitute this operator into this equation, we can obtain this equation. And this equation is nearly equal because there are some constant factors. But anyway, this is a Hamiltonian term containing non-identity operators or public key operators. Let us set the initial Hamiltonian as, for example, 30 x0 plus 30 x1 plus 30 x2. So by starting from this Hamiltonian and changing the Hamiltonian gradually to this final Hamiltonian. So this problem can be implemented by using three-qubit system. So in this paper, we examined the this factorization problem by using three-qubit system, using electron spin as a qubit. So we assume that the three-qubit system as this molecule, this is a factorization molecule, but there are three radical moieties. So this molecule has 3 ampere electrons, so it can be used as a qubit. And in this molecule, we perform the quantum chemical calculation to evaluate the exchange coupling between electrons and also dipolar coupling between electrons. And the calculated value are shown here. And in this case, we use the molecular spin for electron spins as a qubit. So we can manipulate the electron spin by applying the pulse microwave or pulse EPR technique. And we can derive the pulse sequence to perform the time evolution, time dependent, under the time dependent Hamiltonian. This E1, E2, E3 are electron spins. Those are used as a qubit, And these blocks correspond to the pulses. With this shorter one is pi over 2 pulses. And this square one, symmetric square one, corresponds to the pi pulses. By applying this approach, we can obtain the ground state as in this case, the ground state is 3 times x equals 3 and y equals 7. So in this case, the first qubit is one state with the eigenvalue equals -1. So identity minus C0 becomes if the qubit is a 0 state, the eigenvalue of the power Z is +1. So in this case, this term becomes 0. If the qubit is in the 1 state, the eigenvalue of the power Z is -1. So in this case, the I0 minus C0 gives the eigenvalue 2. Also, we can obtain the corresponding the eigenstate by using this pulse. So in this case, we perform the adiabatic quantum computing using a gate model. I mean, these pulses correspond to the quantum gates that perform some rotational gate operation. So here, let us think about the adiabatic state preparation, which is used to generate the Fuchs-I wave function from the Hagen-Fock wave function. So let us think about the time-dependent Hamiltonian. HK is represented by a Hamiltonian of which the eigenstate is a Hagen-Fock wave function. So this is just a Fock operator. And this is a full Hamiltonian, electronic Hamiltonian, without truncating any operators in terms. In order to perform, so if we start from the Hagen-Fock wave function and starting from the Fock operator, and then perform the time evolution under this time-dependent Hamiltonian, basically we can obtain the full scale wave function of the ground state. This is the basic idea of adiabatic state preparation. So in order to perform this adiabatic state preparation on gate model quantum computers, we have to discretize the adiabatic passes like this. So in this case, we divided the evolution, time evolution to m steps. So the time for each step is just a total evolution time divided by m. And then perform the time evolution, quantum simulation of the time evolution under the time independent Hamiltonian at each step. But every step that we use a different Hamiltonian with different st values. St values changes from 0 to 1. So with so in this case, the quantum circuit can be constructed by using this following strategy. We have to divide the evolution time to m steps. And if small m equals 0, this corresponds to the, we set the s equals small m divided by m. So if m equals 0, so in this case, s equals 0. So this, in this case, we have only the Fock operator. If small m equals large m, in this case, s equals 1, so we have the full scale wave function Hamiltonian, or just a conventional electron Hamiltonian. So we set the Hamiltonian as 1 minus s times the Fock Hamiltonian, or Fock operator, plus s times this full scale Hamiltonian. And time evolution operator can be defined as the exponential time minus 1, sorry, exponential minus imaginary unity minus I time Hamiltonian time for each step. So we can calculate that if we have the current function, kind of wave function, we apply this time evolution operator to generate the wave function with the next step. So in this case, we can anticipate several sources of errors. There are several types of errors in the adiabatic state preparation. One is the I call the non-adiabatic state error. This is not unique for the gate model quantum computer, but general for the adiabatic quantum computing. If this non-adiabatic state error is just k equals too short to follow the adiabatic path. And another source of errors is discretization. So step number m is too small, and the Hamiltonian of the m plus 1 step is too different from the that of the m steps. In this case, the change of the Hamiltonian is very large. So in this case, this denominator can become very large. Another source of error is, of course, because we have to simulate the time evolution of wave function. So in order to perform the time evolution, quantum simulation of time evolution, we have to apply total decomposition to construct the quantum circuit. So we have to think about the total decomposition error. So this total decomposition error becomes significant if t divided by m is too long. So time for each total step is very long. And of course, we have to think about some errors inherent in quantum computers, such as the coherence and incomplete operations. And of course, noises from the environment. So let me think about the adiabatic state preparation using the H2 molecule, just hydrogen molecule, with the HS distance equal 0.7 angstrom with SO3G base set. So this problem can be mapped onto 4 qubits because the molecular, we have 2 molecular orbitals, just bonding and anti-bonding. So we need the 1 qubit for 1 spin orbital, so we need 4 qubits. And this bonding distance is very close to the equilibrium geometry. So we can easily anticipate that the Hartree-Fock wave function is very good approximation of the electronic graphic scale. And this is a quantum estimation results. So in this case, I perform the quantum estimation by changing the evolution time t equal 10, 25, and 50, and 100. And time for the single total step is set to be 1, t equal 1. So this means that if evolution time, total evolution time t equal 10, the steps of the number of steps m equal 10. In case of 100, t equal 100, the step number m equal also 100. And this is the energy deviation from the fluxy I. This is the fluxy I line. And this is the Hartree-Fock energy. This the horizontal axis is the evolution time. So we start the time evolution at t equals 0. And if the total evolution time t equals 10, the result is plotted as a red plot. So in this case, we can obtain the ground state by applying evolution time t equals 10, we can obtain the ground state. And this is a square overlap with the fluxy wave function. So because this geometry is very close to the equilibrium geometry, the Hartree-Fock wave function already has very large overlap with the fluxy wave function, about 0.989. In this case, we can obtain the very good wave function having the square overlap with fluxy wave function close to unity, even for t equals 10. So we can say adiabatic quantum state preparation converges very quickly, even for short evolution time. But let us think about the situation if the HH distance becomes longer. So I perform the same quantum simulation with the bond distance equal to angstrom. So in this bond distance, the HH bond is almost dissociated. So we can easily say that the Hartree-Fock wave function is not a good approximation. In this case, I also performed the ASP simulation with the evolution time, total evolution time t equals 10, 25, 50, and 100. The result is shown here. In this case, the Hartree-Fock wave function is not a good approximation. So in the previous slide, the energy gap between the Hartree-Fock and fluxy I is just about the 12 kcal per mole. But in this geometry, the energy gap between the Hartree-Fock and fluxy I exceeds the 100 kcal per mole. In this case, the ASP with t equal 10 results in some deviation from the Fuchs wave function. And deviation from the Fuchs wave function can be very thin if we evaluate the square overlap with the Fuchs wave function. So in this case, the wave function after the adiabatic state preparation with t equal 10 have the square overlap with the Fuchs wave function about 0.97 or something. Of course, this is very high because the Hackett-Fock wave function has the square overlap with the Fuchs wave function about 0.71 or something. So we can say that the wave function is improved by the adiabatic state preparation, but not approach to the unity if the evolution time is shorter. So if the HS distance becomes longer, in that case, the bonding and anti-bonding orbital become closer in energy. So it means the energy gap between the ground and SLS state becomes smaller for longer bond distance. So that's why we have to apply longer evolution time to obtain the Fuchs wave function. This is a very this slide summarizes the total error. Let us think about the same problem, hydrogen molecule, with the bond distance equal to angstrom with exclusive basis. In this slide, I fix the evolution time t equal 100, and just a change. Just changes the time for the single total steps to be 10, 4, 2, and 1. The previous slide, this one is set to the time. In this slide, the time for the single total step is set to be 1. So this plot, this pink plot, is equivalent to this plot. And if the time for the single total step is set to be 10, in this case, we simulate the this time dependent quantum simulation of time evolution with 10 steps. As you can see, this blue line is the simulation result with the time for the single total step is set to be 4. This blue line somewhat deviates from the this pink line. And if we set the time for the single total step to be 10, the result was, the hopeless. Starting from the Hackett-Fock wave function, but because of the total error or discretization error is so large, so the energy varies and converges to the wave function with smaller overlap with the Fuchs wave function than the Hackett-Fock wave function. So we can say that the time for the single total step should be set to be at least 4 or less to follow the evolution adiabatic path. In this slide, in this approach, the initial Hamiltonian is set. I use the Fock operator as the initial Hamiltonian, but different definition of the initial Hamiltonian is possible. The one condition is we can generate the eigenfunction or ground state wave function of the initial Hamiltonian. So in this paper, they propose to use the maximum commitment initial Hamiltonian as an initial Hamiltonian of the adiabatic state preparation. So in this paper, first, we have to find the approximate maximum set of the power operator. So power operator can be obtained by applying a Fermat-Cubic transformation to the second quantized Hamiltonian, such as applying the Jordan-Wegener or Black-Scale or parity basis. So we have a Pauli cubic Hamiltonian described by a linear combination of pi operators. First, we find the maximum set of the Pauli operators by a greedy algorithm, or of which all Pauli operators in the set are commute to each other. So usually in this maximum set of the Pauli maximum commuting set is the Pauli string containing only Pauli C and eigenkey operator. And then use this Hamiltonian as an initial Hamiltonian, and then perform the adiabatic scale preparation. So in this case, the Pauli C, if the Hamiltonian, initial Hamiltonian consists only Pauli C and I identity, the initial state is just a spin up or spin down or single computation based state with 0 and 1. So we can easily generalize the initial ground state of the initial Hamiltonian. Of course, there are advantages and disadvantages of in adiabatic state preparation approach. So first of all, adiabatic state preparation is a technique to prepare the correct wave function. So in order to calculate the total energy or molecular properties, we have to perform quantum phase estimation or statistical sampling of measured outcome, like in VQE. And the advantage is we don't have to know the electron structure of the target system in advance of the computation in detail. So we don't need detailed a priori knowledge of the electron structures. And also, ASP needs polynomial computation cost against the system size. But this is satisfied if the energy gap doesn't depend on the system size. In other words, this is a disadvantage. I mean, if the energy gap between ground and acidic state becomes exponentially small, in this case, we have to simulate exponentially long time evolution. So adiabatic state preparation is very promising because we don't need some a priori knowledge of the electron structure, but this approach is potentially unsuitable for strong correlated system, of which the electron excited state is located closer in energy, with the ground state. In that case, we have to simulate we have to set the evolution time very long. Also, because today's topic is adiabatic quantum computers, so probably you already heard about the D-wave quantum annealing machines. And this is this photo is taken from the D-wave website. In the D-wave quantum annealing machine, the initial Hamiltonian is transverse magnetic field, which can be written as a power X operator. And the final Hamiltonian is Ising Hamiltonian. So the final Hamiltonian is only power, includes only power C operators. So is it possible to perform quantum chemical calculation on quantum annealers? This is possible, but we have to transform the Hamiltonian, proven Hamiltonian, or or Hamiltonian, electron Hamiltonian. We have to map the electron Hamiltonian to the eigen Hamiltonian. An approach to transform the molecular Hamiltonian to eigen Hamiltonian is described in this paper. In this paper, first, of course, we have some quantum Hamiltonian. And by applying the Jordan-Wegener or Bragg-Kitaev or something, we can obtain the Pauli qubit Hamiltonian, which is described by a linear combination of Pauli strings. This Hamiltonian, we have n qubits, n corresponds to the number of spin orbitals, and k local Hamiltonian. K local means that this Pauli operator includes at most k of the Pauli x, y, or z operators. First, we have to transform this n qubit k local Hamiltonian to n qubit 2 local Hamiltonian of Pauli x, y, and z operators. There are no approach to decompose the Hamiltonian to k local to 2 local Hamiltonians, and then perform another transformation from n qubit 2 local Hamiltonian to Rn qubit 2 local Hamiltonian HQ dash consisting on only Pauli z operator. This n qubit 2 local Hamiltonian include Pauli x, y, and Pauli z operators. But we need additional qubit resources, which described as Rn. But if we use the additional qubit resource, we can transform the Hamiltonian to the eigen Hamiltonian, consisting on only Pauli z operators. So this is the equation used proposed in this paper, and this CJK is a Pauli z operator again on the case ancillary theory of the J original theory. And we need some S function. This S function takes care of the sign of the state in the original Hebrew space. So by applying this approach, the quantum chemical calculation using D-Wave machine was reported in 2018 in this paper. They performed the quantum chemical calculation of hydrogen molecule, I think. Yeah, hydrogen molecule, which by changing this R of value. Roughly speaking, this R controls how many determinants can be entangled. So if R is very small, such as if the R equals 1, in this case, we can obtain the Hartree-Fock state. So if R equals 1, we cannot take into account the electronic correlation effect. But if we increase the R, we can take into account the electron correlation effect. So if the R equals 2, the result is something like this. This follows the Hartree-Fock wave function. And here, the wave function switches to the spin triple wave function. probably in the MS equal 0 state. Because the MS equal 0 state. Because the spin triple wave function with MS equal 0 state is a linear combination of up down and down up. So we can take into account the correlation between up down determinant of up down and down up if R equal to. If we increase the R, the result obtained from this machine almost overlap with the exact or full CI result. So we can easily expect that if the spin orbital is very large, and we have to take into account many entanglement between the determinant, we have to increase this R. But anyway, for small molecule, we can perform the quantum mechanical calculations by using quantum annealer. So let me clarify the difference between quantum annealing and adiabatic state preparation. Usually, this quantum annealing usually includes some quantum annealing on gate model, but here I assume the quantum annealing on given machine. In this case, the ancient Hamiltonian is written as just a linear combination of power X operator. So this corresponds to the transverse magnetic field. And the final Hamiltonian is eigen Hamiltonian, or more precisely, a eigen Hamiltonian with two local operators, power C operators. But in adiabatic state preparation, we start from the Hartree-Fock operator as an ancient Hamiltonian. So Fock operator is written as shown here, and the final Hamiltonian is the electronic Hamiltonian. So in this case, this Fock operator is inside of the full Hamiltonian. So it means in the adiabatic state preparation, we gradually include the operator outside of the Fock operator into the time-dependent Hamiltonian. So this is the almost all of the today's topics, but finally, I will show you some recent approach because of the direct calculation of energy gap by using adiabatic quantum computers. So let me assume that we have a time-dependent Hamiltonian, and HD is the driving Hamiltonian, which is the ancient Hamiltonian, and HP is the problem Hamiltonian, which is corresponds to the H fin final Hamiltonian in this slide in my code. And AT is 1 minus HD in the definition. And let us think about the adiabatic quantum computing, starting from the superposition of ground and eclipse states of the driving Hamiltonian. So this is the ground state of the ancient Hamiltonian, and this is a eclipse state of the ancient Hamiltonian. And then perform quantum annealing by changing AT from 1 to 0. So at this stage, we obtain the ground state wave function in the superposition of ground and eclipse state of the problem Hamiltonian, and then perform some time evolution. And then after that, we perform reverse quantum annealing. So if we perform this operation, the wave function after this reverse function annealing is reflected as shown here. So as you can see, there are some phases between the wave function of the ground state and ecstatic state, and the phase shift depends on the excitation energy. So it means if we perform the projection measurement after this protocol and changing the evolution time curve, this is the time for the time evolution. And then perform Fourier transformation, we can obtain a peak corresponding to the excitation energy. So in this case, usually the adiabatic state preparation or adiabatic function computation is performed by using the single starting from the single eigenstate, such as ground state. But if we use the function superposition on ground and ecstatic state, we can obtain the energy gap directly. This is very similar to the approach of the function phase difference explanation I covered in the day 3 of the lecture series. So in this case, the importance is using the quantum superposition on ground and ecstatic state. And this is yes, this is the last slide of my talk. And thank you very much for your kind attention.
Thank you very much, Professor Sugisaki, for the very nice talk. Are there any questions? Okay, so
hello.
Yes.
Okay.
So my question is, why the deviation increases from the full CI graph if we increase the time for single total step? The slide you show for 10, it is actually deviating quite much.
This one?
Yes.
So if the time for total step is very large, in this case, this corresponds to the, this m steps equal 10. So we divide the evolution, adiabatic evolution with 10 steps. So in this case, the total evolution time is fixed as 100. So there are two reasons. I mean, one is the total composition error. If the total, because the total composition error increases if the evolution time for each total step is wrong. And another error arises from the discretization. In this case, if we set the time for the single total step t to be 10, the instantaneous Hamiltonian at t, let's say small m, let's think of this small m. Instantaneous Hamiltonian with small m equal, for example, 3, is very different from the instantaneous Hamiltonian with m equal 2. So in this case, the somewhere yes, in this case, because the Hamiltonian is very different from the previous step, so it means the eigenfunction of the instantaneous Hamiltonian is also different from the previous Hamiltonian. So in this case, in such cases, this denominator becomes very large, which causes the some contamination from the excited state. So in order to perform adiabatic state preparation without contaminating excited state, this instantaneous Hamiltonian should be changed very slowly. So the instantaneous Hamiltonian with m equal 3 should be very close to the instantaneous Hamiltonian with m equal 2. But if the time for the total step become expected to be very long, in this case, the Hamiltonian of the each step is very different from the original Hamiltonian. So this is the reason why the adiabatic state preparation with the longer time steps, longer time for total state deviate from the full scale function.
Thank you.
Thank you.
Divyajyoti has a question. He's asking you to repeat the difference between quantum annealing and adiabatic state preparation if possible.
Okay, so basically the quantum annealing in on D-wave machine, the initial Hamiltonian is include only Pauli X operators. And final Hamiltonian is Eigen Hamiltonian, consists of only Pauli Z operators. So in the adiabatic, so in the quantum annealing on D-wave machine, the initial Hamiltonian is Pauli X and final Hamiltonian is Pauli Z. So if ST equal if starting from ST equals 0, we have the Pauli X operator. And if by increasing the ST value from 0 to 1, the Pauli question of the Pauli X operator is decreases. And question for the Pauli Z operator increases. But in adiabatic state preparation cases, these Hamiltonian terms are also included in the full CI Hamiltonian. So the question for this Fock operator is fixed during the adiabatic state preparation. So this part has the question 1, regardless of the ST value. And but it is in ASP starting from this Fock operator, and the part written in orange color is 0 in the initial Hamiltonian. But if ST is non-zero, this Hamiltonian has the same question, but this term has non-zero question. So basically, in the quantum annealing on D-wave machine, we start from the Pauli X operator, and let's think of some ball, including which is the ball for the Hamiltonian. The ball includes only Pauli X operator. Starting from this ball and applying quantum annealing, we eliminate some Pauli operator from the ball and then increase Pauli Z operators. But in the ASP, the initial Hamiltonian is also in the final Hamiltonian. Final Hamiltonian include the Fock operator. So in the ASP, we include the operator. So included in the full scale Hamiltonian, but not included Fock operator or correction. So basically, the Fock operator includes just a Coulomb and exchange interaction. So the term corresponding the term to describe the electron correlation, we really included in the time-dependent Hamiltonian. This is a big difference. And also, if we, you can easily recognize that if we perform the Jordan Wigman or Black-Sky transformation to generate the qubit Hamiltonian, this Fock operator consists of the Pauli X, Pauli Y, and Pauli Z operators. And also, this full-scale Hamiltonian is also includes Pauli X and Pauli Y and Pauli Z operators. So this is another difference. So starting Hamiltonian, in the quantum annealing on given machine, the starting Hamiltonian should be only Pauli X operators. But in the adiabatic operations, the Hamiltonian includes Pauli Y and Pauli Z operators, as well as Pauli X operators.
Thank you.
Thank you. Are there any more questions? I probably have a couple of questions.
Okay.
You had shown an expression for the anneal time. There was an inequality which went as the inverse of the difference in energy square.
Yes. This one.
Yeah. So the seventh slide. Yeah. Yeah. So I just wanted to know if because let's say in view of real life quantum annealing for quantum chemistry,
Yeah.
because the system is not going to be closed anymore, would the form of the inequality, I mean, is the form of the inequality known for systems that are when the case where the system is not closed, and also is it known when say multiple excited states are present very close to each other instead of one isolated excited states?
So this equation is usually used in the adiabatic quantum computing, and usually in the adiabatic quantum computing, the energy gap between the ground and excited state becomes smaller if the qubit increases. This is generally in, of course, there are many exceptions, but usually the energy gap between the ground and excited state becomes smaller for larger number of qubits. But in the adiabatic state preparation cases, this energy gap corresponds to the energy gap between the ground and excited state of the instantaneous Hamiltonian. So it means that let us think about the Fock operator. In this case, roughly speaking, the energy gap between the ground and excited state in the initial Hamiltonian is roughly the homolumo gap. And of course, the energy gap between the ground and excited state in the final Hamiltonian is the energy gap of the flux I wave function. So one of the advantages of the adiabatic state preparation is that if the number of qubits increases, the energy gap is basically depends on the molecular system being investigated. So could you tell me about your question again?
Yes. I just wanted to know if the form of the inequality is known in the cases where the system is no longer closed, but then there is some decoherence or at least weak coherence. And also if it's known when instead of one excited state like psi j, yeah. We have multiple excited states that are very close in energy.
Yeah. So basically, this is in this case we assume that J is one excited state, but it can be several excited states. So in this case, if the let us think about the strong correlated system with many excited states for the ground state. Of course, the energy gap between the ground and excited states, the excited states are very similar, but usually this denominator, how excited states contribute to the have this is some octagonal term of the Hamiltonian, roughly speaking. So it means roughly speaking, let us think about the expanding the psi-zero S as the linear combination of psi-zero with S. For example, let us think about the K equal, let us think about the S equal 0.5, psi-zero 0.5, the function psi-zero 0.5. Let us think about the expanding the psi-zero is equal 0.5 as a linear combination of psi-zero is equal 0.49. Because the shape of eigenfunction is different from the x equal 0.5 and 0.49. So this wave function can be expanded by a linear combination of ground and excited state. And the question of the excited state is different from it depends on the nature of the excited state. So basically, this is just energy gap and overlap. So if the let us think about the excited state, for example, 5 excited states have the very closely located from the ground state, and every 5 excited states have non-negligible denominator. In that case, we have to make set the evolution time much more longer than the situation where the only one excited state contributes to this contamination. So basically, it depends on the systems. But roughly speaking, this is just inequality. So and also this is not the exact, I mean the approximate one, because it doesn't result in strict inequality.
Okay. Thanks. I have one more question, but I'm not sure if this is somewhat of an experimental question or a conceptual one. It is just that when we work with gate-based quantum computing, it's only very recently that IBM announced a 100+ qubit machine. Yeah. But in annealing, we routinely see well over 1,000 qubits, even the 3 examples that you showed in the table. Yeah, so yeah. I was just curious to know what they choose as their qubit, or how it is even possible in annealing to achieve so many qubits, whereas in gate-based we are restricted to so few.
So in the annealing machine, they make the number of qubits very large, but instead the coherence is very strong. I mean the coherence time is quite shorter for the given quantum annealing machine compared with the gate-based IBM, for example, IBM Q machine. And also the number of possible operations is also limited in the given quantum annealing machine. So in the gate model quantum computers, of course, we can apply, for example, location gate or signal gate or phase gate or something. But and basically, in the gate model, gate-based gate model quantum computer, the gate is capable of performing some universal gate set to perform the universal computation. But in the quantum annealing machine, such universal computation is not possible, basically, because the number of possible operations is type of possible operation is very limited, and also the coherence time is very shorter than the gate-based machines. This is the basic difference between the gate model and quantum annealing machine.
Thank you very much. Thank you.
Okay, I have a question.
Yes.
Okay. So what you described in this adiabatic quantum computation basically depends on the adiabatic theorem. That is, you would expect the system to be in the ground state of the final Hamiltonian.
Yes.
Now, as you know, I mean, this approach called Vancouver, they introduced two new things. One is that it's based on the variational principle. And the second thing is that it has a navigator Hamiltonian.
Yes.
So I think, either one of these two improvements will definitely, or let's say either one of these two additions will lead to an improvement. So both of them actually should give us fairly good results. And that is what I think they had reported. So do you think that's a good approach? And have you tried implementing either one of them?
Yes, actually, in the VQE approach, I never tried. In the VQE, they use the VQE to optimize the scheduling function, and they optimize the instantaneous Hamiltonian to follow the adiabatic path with shorter evolution time. But I think that approach is very promising. But if let's think about the situation, we have many qubits. In that case, the VQE itself becomes time consuming step. I mean, a bottleneck, and because the evaluation of the cost function scales n to the third power, where n is the number of qubits. Roughly speaking, in the case of the evaluation of energy using the quantum Hamiltonian. But I think the navigator using the navigator Hamiltonian is very promising. And of course, the quality of the wave function obtained from the ASP will depend on the shape of the navigator Hamiltonian. So I don't know what kind of navigator Hamiltonian is best for the best to obtain the best wave function. But one thing is, I think that in the Vancouver group, they use the two electron excitation operators as a navigator Hamiltonian.
Well, excitation and de-excitation.
Yes, excitation and de-excitation. So it means the number of quantum gates will also increase, including the navigator Hamiltonian, which raises the computation cost. But I think even if the computation cost increases by introducing the navigator Hamiltonian, if the evolution time becomes, let's say, half of the original ASP without navigator Hamiltonian, in that case, I think that using navigator Hamiltonian is very promising. So So the problem is how to choose the best navigator Hamiltonian. Because in the adiabatic state preparation technique, we cannot include the measurement during the computation. And just we obtain the correlative wave function, not energy, just a correlative wave function. So we have, in order to evaluate the energy, we have to perform the quantum phase estimation to obtain the energy. So we cannot see the result of adiabatic state preparation directly. We have to, instead, we have to perform some post-processing on quantum computers, such as quantum phase estimation to evaluate the energy, or let's say, for example, swap test to using the fluid wave function obtained from the classical computer to evaluate the sphere overlap, or something like some approaches. So I think that adiabatic preparation is is categorized into the STQC algorithm, not the NIST algorithm. And because the quantum circuit for the time evolution is very deep, so it is very difficult to execute on the NIST devices. But so, but anyway, I think that yes, using navigator Hamiltonian is very promising. Yes.
Yes, it has also been tried in other, adiabatic quantum computations.
Yeah, yeah.
I think they use a different name, some guiding Hamiltonian or something like that.
Yes.
Okay. Yeah. Okay. Thank you.
Thank you. Are there any other questions? If there are no more questions, then let's thank Professor Sugisaki for a very nice lecture today.
Thank you very much.
Thank you very much. Thank you.